Thank you. Good afternoon to all of you. Well, in first place, I hope Mindaugas has said nice things about me. I didn't understand him. So I'm delighted to be here. It's not working, okay? Mm-hmm. Okay. So I must be here, okay? Yeah. I was saying that I'm delighted to be here. Thank you very much for the invitation, Mindaugas. Um, For this session, what I'm trying to talk about is about how we face a data tsunami and how can we explore some new measures and methods for analyzing performance in sports. I'm not really health related, I'm more like a sport performance analyst, but some of the things we are using now, I think they can be also translated to some of the problems you are facing in health, mainly the data tsunami that we are facing, and that's what I'm trying to figure out in the next 45 to 50 minutes. Well, I'll start by a quote, a famous quote in 1943 by Sir Thomas Watson. He was the CIO of IBM, well, quite technology related. He was saying that he thinks maybe in the world there was a market for 5 computers in 1943. Obviously, he was wrong. Nope. Technology is really affecting our daily living. If you can say, sorry, it's working now? Okay. And with the evolution of technology, we are becoming different people. We are having much more data in our daily lives, and we are producing much faster evolution in here, okay? And we are dealing with a much faster evolution that we thought and we saw in the previous years. So, going backwards, it's not the strongest of the species that survives, not the most intelligent, but the most responsive to change. That's a very strong idea that we should stick on also into sports. Okay. So, sports coaching has been always an activity with a very lonely characteristics. The coaches were always lonely in their jobs, trying to advise the players and the sports and the athletes on how to perform. It is true that a coach has a very holistic and subjective perspective, but it's a fast perspective, and also he has the problem of having a weak memory and a weak power of explanation from the results he's seeing, okay? So now the coach has been replaced by coaching staffs, and all sports and all professional activities are dealing now with staffs of people that, with some of them with specific roles and functions, dealing with each one with his specific job, okay? So these coaching staffs are producing a lot of data, as you know. There's a coach for offensive problems, a coach for defensive problems, a coach for physical conditioning, a coach for match analysis. There's a coach for every single aspect of the game, for example, okay? So quantity of data is related or somehow related to comprehension, and we started by the lack of information where all was subjective, and we started to quantify the workload. We were dealing initially with, for example, quantifying the heart rates, and quantifying the heart rates and this internal workload as becoming to increase our interpretation and our comprehension of the sports performance. We are now facing also a big and a huge amount of data with GPS and all kind of gadgets that are producing a lot of data. Some of them we are not sure about their validity, and we are now moving to another step of the analysis, which is making sense of all this data and improving, or how improving visualization methods can be in fact very making sense at the moment. So sports now, it's about sensors, fibers, multi-cameras. It's all in real time, it's all mobile, it's all tactile. Things have changed very quickly, and we must react to this change by adapting ourselves to our needs, okay? These sensors and these wearables are now have a different architecture, and they combine several components together and transmit data. We have accelerometers, gyroscopes, magnetoscopes, physiological sensors, all integrated, all transmitting the data to a cloud, and it's really changing the way we see and the way we analyze sports. Inclusively, we have now the Internet of Things to sports also perspectives. And these systems can really optimize the data collection, can automatically process and automatically create customized visualizations for our data. And it's really important because this multidimensional perspective can approach a lot of people and can be a cost-saving process also, because it works and fits the athletic trainer, the manager, the coach, the doctor, all of the people involved in the process, okay? For example, we have now systems capable of automatically detect, extract, and process data in a practice session without any human intervention. Just the wearable is capable of gathering data, process data, and provide for a final result without any human intervention, which is quite an advance, okay? Well, where are we going to end? Well, we don't know. Maybe an eye track as a tutor also that tells the players or the sportsman where should he go, what should he do. Psychophysiological sensors integrated in our skin that also gives us location and performance determinants. We don't know really where are we going to end. And probably we will have such integrated systems that are able to advise us in the most right ways to perform, either in sports and in health-related problems. So, previous to these advances, we are really interested in what happens with the data we collect. If the data is used to inform decisions, and if those decisions really affect our performance, that is our main problem. For example, in football, with this data tsunami, a lot of new variables have come to analysis. For example, the metabolic power is being analyzed in a lot of new researchers, is being used in a lot of new teams, but we really don't know a lot about this new variable. This happens a lot. Technology has evolved, but we are not really sure. We embrace technology, but we are not really sure of what we are measuring. So this new candidate variable, as the metabolic power, for example, which is used maybe for 2 or 3 years ago in high-level teams, in high-level soccer teams, for example, and last week, for example, it was published a study saying that this new variable is not really valid, because if you measure metabolic power as is being used with GPS locomotor variables, and if you measure metabolic power with indirect calorimetry, the results, as you can see, are not really the same. So we are advancing too fast in some of the cases, and we need to slow down and figure it out if the variables we are measuring are really valid in the first case. Another step is to understand if the measures we are taking now are really providing much more information than we used to have. Because, for example, we used to use total distances and partial distances to analyze performance in soccer, and for example, the metabolic power derived variables are not providing much more information than we have previously in our systems. So we are investing a lot in technology, and maybe our investment is not providing sufficiently new information that provides an increase in performance, and we must be careful for that. So, what for? We can measure internal and external workload, we can optimize fitness levels, and you can tailor individual recovery methods, that's true. We can use it also for injury prevention or rehabilitation. We can design new personalized equipments, prevent overtraining. We can do a lot with this new data, but we have to slow down a little bit. Our view is that commercial interests are becoming much higher and are overcoming the need to have a scientific validation of the variables and the usage of the data. Okay? We can use, as we are doing also for tactical performance in sports, with the location systems and the GPS systems integrated in the devices that players are wearing, for example. So, sports analytics are impacting more and more in the players' lives and the athletes' lives, and so we have become from a previous step, which was merely descriptive, to a diagnostic, predictive, and prescriptive phases. We need more data, we need more skills, but we are moving and leaving the past, we are moving to the future. That is, how can we prescribe work and how can we prescribe training based on data that we have about the past? It's not an easy task to do, but it's maybe our challenge for the next years, okay? Because we shouldn't forget that the data we are collecting is data about the past. So to use that data to predict the future or to overcome any difficulties in the future of the athletes, we must be careful with that assumption, okay? So, data. Oh, a Lithuanian flag. One of the most dangerous trends in sports analysis is the illusion that with enough data we can predict the unpredictable. But we can't. Not with all the data in the world we can predict what is going to happen in the future, and things will always be unpredictable. This is also due because of the butterfly effect that tells us there's a really high sensitive dependence on the initial conditions. There is a small change in one state of a deterministic, nonlinear system can result in large differences in a later state. The butterfly effect says that if a butterfly in the north hemisphere spreads its wings, it will provoke, or can provoke, a hurricane in the south. Slightly differences in one state can be tremendous differences in later times, okay? So, for example, in a soccer game, we can have a goalkeeper that makes a pass, and that's a winning goal for a championships, but if he does another pass, it can lead to a lost possession. And that was just a pass difference. There's not any data in the world that can lead to a different conclusion. We cannot predict the unpredictable phenomena. And we should not try to do it also, okay? But being unpredictable doesn't mean it is random dependent. For example, collective behavior that you can see is more likely emergent from local information and shared affordances that players have, and each game situation is unique and unpredictable, but trainable. We have here very, very, very similar situations. We cannot predict, but the agents are taking decisions based on local information, and these situations are quite similar. Okay. So, if it's trainable, we should be able to measure changes in performance, and we should do it with real data. how are we doing this kind of measuring systems? We are using positional tracking with the help of video cameras. They are now available all over the world and all over the sports courts. We are also use the famous GPS-based training systems that are becoming more and more affordable, okay? Although they have some validity problems at higher speeds. So the idea is, can we use this dynamical positional data to measure tactical performance? And I will tell you about some of the methods we are using and how can they be applied eventually to a more health-related problem. So our jobs as embedded scientists is more like collecting, storing, and processing high amounts of data to improve communication, that is, how visualization enables us to translate immediately the information to coaches, and how to provide them for alternative perspectives. So basically, the system can give us, through the time, data like heart rate, speed, distance, and now we are using also the locators in X and Y axis, okay? So, just for you to see, how many data are we talking about? For example, for one player that we can gather 15 hertz data, just location data for a 90-minute football game, for all the players we will have 3,005,064 data points just for the 22 players in the football pitch, okay? And this is just to start all of the tactical based variables. We will have then the heart rates, accelerations, decelerations, impacts. We need different hardware, we need different software, and we need different methods to process this data. We cannot use any standard deviations or average values just for itself, okay? So we are using not only the traditional or more traditional SPSS or Excel based methods, we are using programming in MATLAB, programming in Perl. We are using a lot of R, statistical programming also, and some network that I'll show you later with Cytoscape or Node XL to provide some of the network configuration of football teams, for example, okay? So, can we use this dynamical positional data to measure the tactical performance? And which variables can we use to measure this performance? Just for you to have an idea, we have the players' locations, and we can use the team centroid, which is more or less the heart of the team, the distance from each player to the centroid, the average distance, it's called the stretch distance index, the average distance from all players to centroid, and synchronization between players. One of the most interesting approaches to process this kind of data, because as you can see, there's a lot of complexity patterns in this approach. These complex, dynamic, and nonlinear patterns can be analyzed, for example, using approximate entropy, which is a regularity statistic that quantifies how unpredictable is that time series. That means how unpredictable, for example, is the player playing. The basis of these data processing methods is that we have a signal in the time series, but we also have noise, that unpredictability. We should account for that unpredictability within our models of analysis. Our traditional models of analysis are only analyzing the signal and getting away with the noise. But noise is part of human signal also. So we should not get rid of them, okay? So for example, a more predictable series is the result of better positioning in the pitch. The subjects or the players are not playing so randomly, but are committed with some kind of internal organization.
I'm showing you an example of a study we have carried lately, a pre-test playing football on a 5 versus 5 small-sided game, where the players were aware of how to play football, how the tactical performance was. Then we teach them how to play in 26 hours, and we have performed an identical post-test. Our idea was that increasing expertise will increase predictability. That is, the players will become more predictable with more expertise in the game. Okay? We have analyzed the distance between each player and team centroid, for example, and entropy values are showing us that in the post-test, for example, the players were all much more predictable. And that is telling us that players have less random behavior, and the positioning now is more rule behavior in the post-test. I tried to figure it out in the more health-related conferences, if this kind of approach could be used in health-related problems, but in fact, approximate entropy was a data processing method developed by Pincus, which was a researcher mainly devoted to study heart rate dynamics. So there's a lot of research in heart rate variability, for example, that is showing us, as you can see here, that healthy persons and depressed persons have a really completely different profile of entropy in his behavior. That is, you can not predict so accurately the signal of heart rate in healthy related persons. Depressed persons become more predictable in terms of heart rate fluctuations. That is really logical because we are living in a really dynamic environment, and our heart needs to adapt constantly to the environment. So the signal is much more unpredictable than a depressed person who really doesn't care much about the environment, so is not so responsive to those changes. Okay? We can also study synchronization between players. How can we measure how the players are coordinated if player number 1, for example, approaches the team center, player number 5 also approaches, player number 5 leaves the center? Are they related and coordinated? This is another question for study synchronization. And we use to do this the relative phase, which is a signal processing method used mainly by engineers. We can have the data showing us coordination in phase, that is, the signals have the same direction. If one player approaches the team center, the other player also approaches. If one player leaves the team center, the other player also leaves. That is, the signals are moving in the same direction. And you can have an antiphase relation, which means if one player approaches the center, the other one will leave, and vice versa. Okay? So for this study in football, we can have a pre-test coordination pattern that shows basically that the players are really not coordinated. This was before they played the tactical lessons. Okay? Afterwards, in the post-test, we can see that players showed a very coordinated behavior, mainly with antiphase and transitions, meaning that if player number 1 approaches team center, player number 4 leaves. And so they maintain the occupation in space. Okay? So this is really a nice way to see the effects of training without getting rid of inconvenient data, I will tell. Okay? So players now are becoming different playing the same game. Okay? You can find the same technical processing methods, for example, in a study published recently that shows us that the aging process leads to less complex process and people. That is, with age, we lose coordination and we become really more predictable and more coordinated instead, okay? So, any more statistical techniques that can help us to reach a higher level of understanding of such amounts of data we are gathering? We can also think about clustering techniques, for example, which allow us to see the big amount of data and their relations in another perspective, using, for example, automatically created groups. We have done also recently a study in which we use football players from different age range, and we try to have from them as much as variables as possible. And with these variables, our idea was to classify performance automatically and use that data to split them into different groups, only based on performance in actual training sessions. So the analysis has allowed us to constitute 3 different groups. They are all very similar in age. They are all very similar in other variables, and these different groups were mainly constituted because of their performance in body load variables, in distance, in higher intensity zones, so we can also quantify how the weight of each variable was important to classify the subjects. So at the end, we can have 3 different groups according to their field positions, and we can identify where is each player according to his initial conditions of performance. At the end, we can mix in the training sessions players from 15 years old with players with 17 years old with players from 19 years old, because their performance is quite the same. So this is quite experimental work, but it allows us to use data in a very different form and allows us to constitute training groups in a different form, which is really more effective than we used to do it, okay? Because previously we do it with the coach's eyes only. The coaches would have seen that, for example, a 15 years old player could be training with a more advanced group. But now we are using it with data, with real data, okay? We can use also discriminant analysis. Discriminant analysis can allow us to use the training sets to classify the cases into well-defined groups. I can show you also an example in basketball that we have done recently with an analysis of 1,230 games, 41 variables. That's a lot of data. It's a whole NBA season. And we try to figure out where are the differences between NBA all-star players and non-all-star players. It's really a lot of data to process with traditional methods. So we have designed the model, and we have a model for non-all-star players and a quite different result for all-star players. Meaning that at the end, we can take a profile, a statistical profile from a player, and with this algorithm, I can tell you that he suits better the all-star profile or the non-all-star profile. That is, you can also move a little to talent identification process. We can also move in here to evaluate more concretely the value, the financial value of a player, because this is more objective. This is more objective evaluation. Okay. And we also, in this study, we also classified the performances automatically. That is, all NBA players can be classified into different groups according to their specific positions, according to their impact on team performance, and we have done it also with cluster analysis in this study. For example, we can have here cluster 2, which is a very different group because it has 4 players from the NBA first team and 8 all-star players. And you can have here cluster 4, also very different from the other ones. And you can see that in cluster 4 we have 23 guards, which are different from all other performances in the league. And it's really nice to have such methods because at the end you can identify where each player is. Each dot is really a player. So you can see how they have unique characteristics and how you can help them and how you can personalize all this kind of work. Okay? So at the end, I was telling you about also about data visualization. How can we visualize better our big amount of data? We can use networks, for example, that allow us in a single graph to understand 1, 2, and 3 variables at the same time. We are looking right now at these 2 graphs. They are representing almost 7 million of data points, which is a lot of points. And you can see, for example, the between score that tells you if the player is crucial to maintain the team passing connections. These are only passes, okay? And we have the closeness score. How easy it is for a player to be connected with their teammates. So in this graph, we can see 1, 2, 3 variables in simultaneous. We have here passing density. More dark means more passes. We have here the between score. More dark is more between us, and the closeness score. Bigger the circle, bigger the closeness. One team, another team. That is, in one graph we can have the representation of millions of data points. Okay? Traditional heat maps, we can see now a heat map not from the player's positioning, but from the ball positioning in each game quarter. You can see that, for example, Chicago Bulls have performed most of his offensive patterns from the left side in the first quarter and from the right side in the second quarter. Very different profile in the third and in the quarter. You can see that the ball is more near to the basket in the fourth quarter. And with this kind of information, you can really approach the coaches in a different way. Okay? All of these are really static methods of presenting and visualizing information, but we also have to move to dynamic methods. Okay? So we can have, for example, the effective playing space. You can see how the team behaves in effective playing space. You have here the square meters. You can have here the percentage of the pitch that is being really occupied. You can have here the difference between one and the other team, and then you can have the percentage of uncovered space. And with all these tracking variables, you have all this data immediately to visualize, and the coaches with the players can use it any way they want. Okay? Oops. Yeah. You can use different data processing methods to quantify where is the leader from a team and who is following that leader in terms of velocity of displacement. These are methods originally developed to study fishes and birds, and now we are using this with football players. It's really interesting to know because some of these leaders are really not statistical leaders of the game, but are statistical leaders of the team, as you can understand. And almost the final processing tool to understand this is, because this is really interesting for the players and for the coaches to see and to analyze, but at the end, they want to see themselves. They want to see themselves playing, and if you can combine data processing techniques with video analysis, that's really probably the state of the art that we are going to achieve. Something like this. You have the game, and you have the previous analysis in simultaneously. Okay, you can see the leader following relations. They are coming and appearing. The ball here, 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 here. So along with the video, you have thousands of processing points and processing techniques that allow us to understand better what's happening. Let's wait for the goal. Yeah, okay. So as a final remark, I will use Ian Lemur, my friend, training tips which are really important, and I think they are really meaning. Give fast feedback to players. Really important. Also important, show players the session RPA scale post-training. That means without technology, we have the players' perceptions are still very, very important. Don't ever miss that, okay? Show players how monitoring can help their own performances. Show them, okay? Make sure the players know why are you collecting the data, because some of them don't know. Create a consistent routine in order to be consistent. They must expect and they must be organized for each day. And report few variables, but collect many. Okay? Along with this, I also borrowed from Mark Simpson my take message for today. Let the development areas and limiting factors of your athletes determine your choices on technology. Don't buy technology just because. Determine your needs and then go for the technology that suits best your needs. Okay? Reduce the gap between how much data you produce and how you actually use. That's also a key. Actively reduce the number of charts and tables you produce to coaches. If you can give them a meaning, one-page chart, better than a 50 pages report. Okay? And at the end, confidentiality is paramount. Data we use from players, data we use from any practitioner should be anonymous. We cannot use that data for other purposes. Okay? So, thank you very much for your attention. That was my final message. Thank you.
Gal būtų klausimų. Žinau, kad garsas nebuvo labai geras.